Welcome to today's presentation by Perry Perendo in the Ascendo Reliability Webinar Series. Perry and I have been talking, Perry, I think it's been a number of years about design of experiments and quality statistics and a variety of topics. And I'm very happy to have you join us with the Ascendo Reliability Program. So welcome, Perry.
Thank you, Fred. I appreciate the opportunity to share with the group.
All right. And I think your slides are up. The chat window will remain open along with the Q&A window. And as we get questions that seem like would be good to interrupt you, I'll go ahead and do that on behalf of folks. Also, if you notice anything in the chat window or Q&A window, please feel free to chime in with that. And let's see, we've got recording going. We got the windows all going. And I should check one more thing though, Perry, does anybody else hear us? If you could hit the chat window and let us know if we're coming through all right.
Good idea.
All right, thanks, Joseph, Mark, Natalie, great. Brendan, yeah, it's always that moment of hesitation, Perry. We always want to make sure that there's so many different things that could go wrong. All right, so Perry, I'll hand off to you and take it away.
Sounds good. And I'm seeing the comments about being a little quiet on my side, so I'll speak a little louder as we go. If you do have problems, I can pick it up a little bit more. But yeah, again, welcome here today. You can get information, as Fred mentioned, on my website, more of my background, or maybe you saw it already. In the chat window ahead of time, saw a few comments about people's background, and George Box is someone that I've certainly read his stuff, and I talked to him prior to even beginning training, and I've been using DOE over 30 years now, and when I started training 20 plus years ago, George is one of the first people I contacted to talk to. So we'll talk about some of his references and his contributions as we go through. So anyone that's heard me before or knowledge of my background knows that anytime I do a talk about any topic, there's always more what I feel critical things than time allowed. So we'll keep this to an hour, but at the same time, I'm trying to pack a lot into it. The goal here is to just give you a very high-level exposure to DOE in an hour, just some of the key phrasings or language, trying to be practical about it as well. And as we go through, certainly as there's questions, I'll be monitoring the chat window. We can do that, but my whole approach, being a mechanical engineer, is being practical, making my job and development easier. So that's the title for this session, is Practical Application of DOE for the Development Process. Whether you're developing products or hardware, or products or manufacturing processes, the concepts here all carry over to both. But it's the upstream versus the troubleshooting, problem solving focus is where I've spent most of my time. So the idea is how can we develop faster and better with design of experiments? But part of that is understanding, do you need design of experiments with what you're currently working on? And when should you want to use it? Because I think those are more critical than the tools themselves. So to kind of walking through, start with the definition of what DOE is, for those of you that might not be that familiar with it, and that's where I'll look for some chat window engagement. Walk you through a case study. When I first talked to George Box, one of the things he commented was, before you tell them anything, give them a case study so they know why they should be listening. And then a little segment about, do I need design experiments with the type of work I'm doing right now, or this task on my project, do I need DOE? And I have kind of three segments of that. And then, do you need help, or is this simple enough to do on your own? And if you notice, each of those sub-bullets have a DOE phrasing to them. So it depends on experience, depends upon experiment, and then degree of effort, and then depends on expert. So to go to the engagement slide here, when you hear DOE or design of experiments, what does that mean to you? What's your quick definition? So if you can throw something in the chat window, I'll kind of read those, just to kind of see where people are thinking. Obviously, I'll give you my own. I'll kind of talk through this as you're typing a little bit. Obviously, I've taught this at the college level, and sometimes it's a required course for certain majors. And I've had people day one think that DOE stands for Department of Energy. And so obviously, the Department of Energy is not what this is about. By the acronym, DOE is Design of Experiments. So what I'm seeing, statistics, plan experiments to prove your concepts. Someone that's completely new, which is great. Control of variables, controlled experiments. Minimizing the number of tests, I like that one, Joe. Designing tests with smart combinations of variables. Yeah, so so if you're brand new to this, that I've designed it for that, but also if you have more experience and with the definitions I see popping up, we'll hit some of you that really have a good idea about this as well. And Sean just had one, excuse me, as well about understanding basically the impact of changes. Yep, relationships. So with those and if you have more that you want to share or finish typing, certainly I'll read those. Those come up. Let me give you my definition. If you have download the slides, you'll see this in there. But to me, DOE, my definition, and when I first started training, the toughest thing was to come up with a good definition. I think it's a testing tool to assist in the process of understanding a system. There's a lot of kind of wordy ways to describe DOE, but that's really what it is. And going through those, I have a video out on YouTube that goes through this definition the similar way I'll go through now. But DOE is a testing tool. So it's used in that testing process. And so that's what people, obviously with the word experiment, get into. I like the word assist because DOE doesn't give you answers. It helps you through the process of learning. And so that's, again, where hit some of the other part of this definition is you're trying to gain understanding. And I think that's an important part of this. As people put in, it's understanding how things work independently, how they work together, how it impacts the performance of a system. But to me, ultimately, it comes back to understanding that system. And when you gather that understanding, that's what leads to improvements in your product or your process. So with that definition kind of in mind, and the other ones you said, I didn't read anything that I felt were incorrect. Just different ways to phrase similar idea with different levels. So when I do a DOE, I talk about a process, and we'll show you briefly that process. But I start with a goal. And to me, the goal is the words of why are you testing? What are you trying to learn? In this particular case study, and I can't disclose who I did it for or much of the technical details, but this will give you the essence. We were trying to cool a motor being used in a device, but also do it quietly because the user, the operator of the device, didn't want a very noisy system. So the goal in words we want to quietly fan cool the motor on a device and do it right the first time. Historically, it was something that was a pain and went through a lot of redesign, a lot of delays in the development process. So all that would be the goal. It's kind of the background, but it's really why you're doing this test. Why do you care? What's been the trouble you've had in the past? And I think that goal and words like that is an important first step in setting up a project. So the bullet below that, the second step in the DOE process, is the response. And in DOE language, that just means your output variables. And this one, it's maybe slightly obvious, but it's the airspeed. So we wanted obviously to cool it, which would be temperature, but we had done enough modeling to know if we got a certain airspeed or air velocity that we would cool it appropriately. Temperature measurements are pretty transient, but airspeed, we knew through modeling, it'd be a little bit more consistent to measure and quantify. That's how we did that. And then the noise in decibels, which maybe is a little bit obvious, but ultimately defining that output was critical because it was a series of microphones to pick up the noise in different angles and different spots. And just the way that noise in decibels wasn't just one microphone in one spot, it was a matrix and a 3D problem. In fact, 4D if you consider we were measuring it over time as well. So in DOE language, in my process, the response is the second thing that we focus on. And then the third part is the input variables. They call that factors, but we want to identify those variables. And that gets in the details of this, which to me are less important. The next step of the DOE process, the fourth step in my approach is, fourth step in my DOE process is how do we approach this? How do we set up our test? And this could be a DOE if it's appropriate. And obviously, this is a DOE webinar, so it is. But in this case, we had multiple fan vendors telling us their design was really good and here's why. So we wanted to explore those different fan designs plus other installation parameters using design experiments. Obviously, one of those was the speed of the fan, or rotary speed, but also those multiple designs. And we wanted to determine if a window of operation existed where we could optimize and hit our objectives. And if because we had three fans, we were hopeful one of them would work, but we needed to know if one of the three would work, two of the three, or none of the three. So that was our basic approach. And again, the different fan design was one variable, speed was another, how close the fan was to the wall of the device was another. Is it that compartment it was in? So that was kind of our approach. And we did a DOE for each fan for two reasons. Number one, I think any test DOE that's run on different concepts needs to be a different DOE. And each fan was so unique that we felt it was important to separate them out. Second thing was the delivery date from each vendor was unique and certainly not guaranteed. So we wanted to be able to complete a DOE analysis for each fan. And if we only got two of the three, we could be complete. If we got all three, that's great. If we only got one, we could still execute our test and not be dependent on fans showing up or not. Result of this, by changing all those things, and as you saw through the chat window, some of those definitions, we're strategically changing our input variable combinations so we can understand that relationship to the response of the output variables. And we had several output variables and several input variables. So we co-optimized that through a process of optimization. And our end result, we found a window of operation that worked prior to building our first production part. So we did this on the bench, and it eliminated that need for the custom noise reduction components which basically meant stuffing a bunch of new insulation into that compartment, which was from design time and procurement time and retest time was a 3-month process. And in doing all that, typically it took 2 to 3 iterations. So this is a typical 6 to 9 month delay at the end of every R&D effort. And we were able to get this in basically a 3 weeks of testing. And actually it wasn't even that long. It was a week of data collection and then a couple weeks of analysis and discussion of what to do next, and then getting all the fans in. So it was 3 weeks calendar, but 1 week per fan. So we were able to do that. We did not have that redesigned, so we saved them 6 to 9 months at the end of the project and got it launched on time. The other long-term impact, we obviously improved time to market. We also had a predictable end time of the project, so the next project could start up smoothly. We learned enough here, so we knew which fans would be more appropriate for different air speeds or different systems we were designing, different devices. It also set the company's standard for design of this kind of product, continuing to recognize the benefit of this DOE approach. So as they had a new application, they would run this same DOE setup, analyze it, and then find that sweet spot, and that's what they would do on the bench. And this is 15 years or so now, they've been using this approach without having to go through the redesign process. It's always designed right the first time. This graph that you can see on the right-hand side of the slide, this is an example. You can see our X and Y axes are a setup variable we had and fan speed. Then you can see our response here. The kind of diagonal lines are the airspeed. And then the horizontal line in this case is our noise limit. I just showed 68 decibel. We gave a window for airspeed, knowing if we were in there, that's probably the window that we would perform well. And the yellow area is the overlap between those two responses. So the opinion was, based on this empirical knowledge, if we operated in the middle of that yellow zone, that was going to work, meet our noise and our airspeed needs. So you can see there's a lot of gray area which would not meet the requirements. So knowing that up front, hitting the middle of that sweet spot in the yellow in the bottom, that was our design point. And so we had what I call guard band, or some error tolerance. In case we were off a little bit in our empirical, we could still meet these specs. That's just a quick case study. So again, here's a chance to ask another question of you, and this not thinking about DOE, but in general, when you're testing, why do you test? What's the purpose? What's your intent, or what are you trying to accomplish when you test? Yeah, Dennis asked a question. Noise being less than 68 decibels was our objective. And then the airspeed window is, yeah, those are the performance targets. Those are the specs. Mark asked a question, which is very observant. The y-axis goes from +1 to -2. And usually a DOE is from +1 to -1. And what we actually learned from this DOE was that the performance recommendation window that we were given wasn't going to meet the spec, and we had to stretch the spec, not the spec, the performance variables, the input variables, we needed to stretch those outside of the range tested to create a yellow space. Even though that's extrapolating and a little bit dangerous, that's what we did, and it was a little dangerous, a little risky, but we also knew that in the area that people felt we would find a solution, that was all gray area. And to hit the middle of the sweet spot predictably or predictive, we had to be outside of our engineering guess of where we should operate. And when we did that, it actually worked right. So that's a great, even though it was risky, it ended up turning out for us. But obviously, we did another confirmation test before we built production units at that setup. Sean asked, what's the setup factor in this example? The setup factor in this case, and there's a couple installation parameters, the setup factor, and there's more than just what you see, but the setup factor is basically the distance from the fan to the wall of the device. So if it was offset a small amount or a big amount, how could that affect the airflow or the noise? And Dennis says, yeah, the example had multiple response variables, which is noise and airspeed, and had multiple input variables as well. The ones shown in the graph were only two of them, which is fan speed and the setup variable, which is Sean asked about. So Rupesh talked about, is it for a known issue or an unknown issue? And I guess, thinking about what's the purpose of your test or why do you test? I'm going to relate it to that question. Sometimes people test to confirm knowledge, and others are trying to acquire knowledge and basically see what would happen. Science or experimenting or, again, doing trials. So yeah, whether it's a risk or an unknown situation or a known situation, DOE can help. Again, you can use DOE in a root cause analysis for a known issue, or you can use it to gain understanding for a risk in a development process. Yeah, so Rohit talked about simulating potential root causes. That's certainly true because you want to understand. And to me, root causes are key input variables. So you can learn that through a DOE. Mark talks about validating an analytical model. That'd certainly be another one. Give a reliable and correct answer to a problem. Dennis is asking about the ability to design or build multiple prototypes. And we'll don't have my model for talking about that in this presentation set, but if you build I mentioned before in the case study that we did this testing on the bench versus building a full-up prototype. And so you look at your risk areas and you can mimic that realistically on the bench or some subscale, and then understand it at that subscale level and then put it back into your overall system. That's affordable. But if you're looking to, say, build a Boeing 747 aircraft to test on, that's going to be very expensive. But if the issue is with the release lever for the seat so you can recline, well, now we can just do something on that lever and do our testing there. Yeah, I've never had places that just have an unlimited budget will throw money at building multiple prototypes. But if you can focus it down in the area of concern, then that's where you can do your iterations in a more cost-effective way. And Daniel talks about testing to learn. So Dennis asked a follow-up question. So validating components rather than the entire system. And let me spin wording here a little bit. To me, validating, you validate a system to confirm it meets requirements. You learn and develop components. So if you learn about how the input variables affect an output variable at a lower level, and you understand how they work, and then you go verify or validate it at a higher level with the learning or understanding that you have. So and let me jump to the next slide here. I think this will explain it. Why do you test? To me, it depends upon your experience of the type of test you're going to do. You're testing to gain knowledge. More knowledge reduces project risk. So if there's an area, if you've done failure modes and effects analysis from a reliability point of view, and you have a high risk area, usually the high risk means you just don't have a lot of understanding or a lot of knowledge about it. And so we're testing to gain knowledge of that. So if you don't have a lot of experience with something because of lack of knowledge or because it's high risk, then that's a great place to do DOE and do what I call development testing. The second sub-bullet here, though, would be, find my cursor. If you do have some knowledge, and I'll call it from other people's experience, maybe it's through physics or science or textbook equations, then you have knowledge, or at least you believe you have knowledge, and you're going to use those equations, you're going to use those computer programs to design something, and then I hear verify and validate. To me, I put those in a similar category. You're going to confirm, though, that the physics or the science and the equations that you used were accurate. And that's a pretty simple test. And talking statistically, just briefly, that's like basically a t-test. Does it match that expectation or not? It's or process capability type test. But if you try and do that verification test and it falls outside the window with one prototype, one design setup, then you don't have the knowledge that you thought you had, and you're back in this, we confirmed we don't have the knowledge we have, and we need to go gain that knowledge or create that knowledge because we have a risk of uncertainty or lack of information. So to me, that's why we test, is to gain knowledge, but either we have the knowledge and it's a verification validation test, or we need to acquire the knowledge and it's more of a development test. And a development test, which is the top bullet, a risky area, is where I think DOE fits best. That's the point of this slide or this point is to understand which type of test you're doing. If you're doing a lot of validating and verifying, DOE's not appropriate for that. But if you're dealing with risky areas and knowledge gaining areas, that's where DOE really comes into play. Or, like they've done in the FAM example, I call it they kept hitting the wall. They kept designing something that wasn't working right. They'd play with it, play with it, play with it, finally it would work. They'd design the next one, play with it, play with it, play with it, finally it would work. And those were all verification or validation tests at the production level that failed versus doing a subscale bench test quickly, inexpensively, gaining the information so when they built the validation piece or verification piece, it would work for them. So and this kind of comes back to what we just talked about, but if I test, do I have to use DOE? Why do I need it? And this slide is talking about, it depends on your experiment. If your situation asks, and these are key questions, because I get to ask this a lot, how do I know my project's a DOE or not? You're in a situation where you're asking the question, well, what if we changed this? What would happen? And then someone says, wow, we changed temperature before and it didn't really impact anything. Well, what if we changed pressure? What might that do? And if you're kind of debating this and never coming up with good answers, and they come, well, what else could it be? What else could be going on? Then you probably don't have the required understanding, and you'll most likely need a DOE to get through that. If there's no obvious what if answer, then it's probably some combination of variables or some sweet spot, like we saw in the FAN example, and I believe it was Mark that said, we were actually off screen, off the scale, because our what if and what else questions they had been asking before, they guessed all in the gray zone, and they needed to be outside of the window they felt would work right to actually find a sweet spot or that yellow overlap area. So if you're asking a lot of what if or what else questions, that shows a high risk, a lack of understanding or not inadequate understanding. But on the second bullet, if your experiment is proving you know something, again, validation, verification type tests, I don't think DOE makes sense in those environments. And I see people force it in there, and that's when DOEs do become inexpensive, or it's very expensive, very inefficient, and management will really get upset that you are using DOE because you've used it in an inappropriate place. It takes a lot of time when you're trying to validate and just prove that it's working right. And again, for example, as I say in the sub-bullet, if you have high confidence you're applying well-known technical principles, you've done this and been successful before, that's a simple confirmation test, and that's all that's required. You don't need the complexity and expense and logistics involved with a DOE. But if you don't have that, and you're uncertain of your solution, and management is getting frustrated with the delays, you need to find a way to isolate the risk area, do your DOE testing there. And this is just a picture to help think about that. As people, when I first started using DOE, I was talking to DOE experts, DOE consultants. As part of the reason I went into this myself was because so many of them I felt were pointing people the wrong way and making it too complex. But the phrase I got from people was, anytime you test, it has to be a DOE. And that just felt wrong, and that's when I came up with this little model. If you look at the y-axis here being the performance of your system, that's your output variable. Maybe it's airspeed, maybe it's noise and decibels. And then this is calendar time, working on your project on the x-axis. Early on, you're going to be able to make some guesses, and assuming higher is better, you're going to make some guesses, and you're going to move up this performance curve, and those are easy gains, and I call those verification tests. Verification hypothesis to sound statistical. And you don't need DOE at that point. You're smart, you're educated. Dennis just says low-hanging fruit, exactly right. And you can easily move up that. And that's a horrible place for DOE. But as soon as you hit what I call the wall, and again, you're not making progress, and yet time keeps elapsing, you need to try something different. You're not making the progress like you expected to from your science and your experience. So when you hit that wall, and it's not always easy to define when you're in the wall, those words I gave you, what if and what else, you hear those being used in your conversations, that's a point you've hit a risky, unclear, unknown area. If you apply DOE at that point, roughly at that point, then you can continue along that performance curve and obviously, hopefully, continue and be able to meet your spec. If your spec is super high, DOE will help you progress on that performance curve. But if your spec is super high, you may need a new concept or a new curve to bring you in that spot. But DOE is the only way I've found to continue along those difficult developments and really squeeze out performance in systems that are challenging. If you keep this picture in mind, I think it'll help you identify projects and timing. Even though this may be high risk, you may play with the high risk thing first before you start your first structured DOE, because you need to play with it on the bench at a subscale level, play with it there first to get those easy gains out of the way, and then push on up there with DOE. Hopefully that makes some sense as far as thinking about areas where we already have knowledge versus areas we have risk. And even if we do have risk, there's still a stratification of early on, play with it, later on, do the DOE to continue if you haven't met your specs. What can DOE do for me? It depends upon the degree of effort you put into your test. Um, Typically, and I'll show you some of the tools of DOE, but usually if you want more information and have more input variables, it's going to increase the number of your tests. There's ways to reduce that using some certain tests. Those of you familiar with DOE, fractional factorials can help reduce from doing every combination of the input variables. But in general, what can it do for you? DOE helps reduce the number of tests to achieve the level of information you need to describe the relationship between the input and output variables. Again, multiple inputs, multiple outputs. If we do this right with DOE, it's going to, and pick the right situation, it's going to reduce our schedule, our cost, reduce our risk, improve our probability of meeting requirements. Again, it only goes as far as the concept that you have will allow it to go. And the information obtained is limited by the number of tests conducted. But this is far more efficient way to, with the same level of confidence, gain the information about your inputs and your interactions between inputs, the synergy between the inputs that you have. If you put in more effort from a DOE point of view, you can get more information, but the DOE effort will actually be less than conventional testing, what we call one factor at a time or scientific method. If you just guess one change at a time, that's a very inefficient way and very low confidence way of getting from point A to point B in your development, particularly when there's a high risk, lack of uncertainty, or lack of certainty, lack of understanding situation. So DOE can do a lot depending upon how much effort you put into it, as far as number of tests conducted. I always think it's interesting for folks that are fairly new to DOE to see the range of projects that DOE can be used on. I was teaching, most of my career was actually in the corporate world. The last 11 years I've been consulting full-time on my own. But along the way, I was just an adjunct professor teaching one class a year, that class being a night class in design of experiments. So this is from that 20 years of teaching. This is the list of projects that students did as a part of the course and presented to other students. So from welding, heat treating, adhesives, plating, soldering, laser cutting, electronics, control systems, reliability, manufacturing simulations, computer analysis of hydraulic, thermal, and molding processes. So just a ton of different examples. Over the nearly 20 years of teaching, this was over 200 projects. And on the order of taking out the big projects, we had a $4.9 million project and a few other big ones. But taking out what I thought were outliers, there's about 7 outliers that were huge I took out. But if they had a $0 benefit, I kept them in. 200 projects with about 9 million total savings just in class projects. That ends up being over 40 grand a project for beginners. People with the type of mix I see from the chat window in here. Rupesh asks, is it applicable for embedded and application software? I would say yes. If you're doing a piece of software that is doing a process, a step, sequence of operations, not necessarily in that, because it's just verifying the steps all happen. But if there's variables as a part of it somehow, I think of, you know, multiplier numbers that you add into certain routines to control an output. The control systems, things like that. And that type of application software could use it. I think there is a place for it. Have used it as well for interface screens for a user with a piece of software, looking if you give them warnings or if you give them basically what's their accuracy of doing the right next step and see if and what their response time is. There's an accuracy and response time to color selection, location selection, going through a typical excuse me there. You're going through we set up a standard simulation of operations that we could control, and just by that computer layout screen, we saw which layout, which color scheme would be better. So that was gaining knowledge about our color choice. Even though there's recommendations, we read those, and there's a few gray zones and a few opinions. And so we use that there in layout, but also in the selection of some of the lines of code as well. Dennis talks about DOE is usable in manufacturing processes for sure. Casting, yep, and that's one I've actually done personally. Aluminum casting defects. Certainly for field failures, a lot of that. In my medical device work with recalls, those are big, and I'm promoting using it up front in the development process, so you can hopefully avoid those field failures or manufacturing defects. Customer site related issues, yeah, there's just a ton of places to use it. So I give you this list because these are student projects. These are none of these are my consulting projects. These are just starter places, give you a wide range of where people used it. And software kind of gets buried, electronics, to me, electronics and software is somewhat related, and then control systems is where students played with it. Oh, Hall sensor. Yeah. Dennis talks about a Hall sensor performance, and I've done some proximity sensor design and installation renders with that too. So hopefully that gave you a flavor for if you'd need DOE for a project or not. It's the risk areas, but even in the later stages of risk areas where you've played with it and have hit that wall. But is DOE complicated to use? And we obviously don't have time in this webinar to go through what all is involved, but I want to give you more flavor than I have so far. But to me, the whole, is it complicated, depends upon the expert you use. I put expert in quote because I still don't consider myself an expert. I've done this for 30 years now, DOE, or over 30. And I'm always learning new things and new techniques and new tricks to make things a little bit better, a little bit faster, a little bit smarter. Even though I've coached hundreds of projects and worked with just tons of companies, I still have stuff to learn. And why the experts is in quotes is what I find too often is there's experts that are either too engaged in the mathematics and not in problem solving, or they're an expert only by name and not by really having experience with it. They don't understand problem solving. They kind of have a really set, rigid construct that they work within that it just doesn't work. So, and I've just seen all kinds of those, and that's ultimately why I started consulting, was because I found too many of those. So what I'm going to say as far as, is it complicated? Take some time to learn the details of kind of what the math is doing and what the software is doing if you're using software. The overall foundation for DOE is actually very straightforward. It's important to understand and follow a simple process, which is I've kind of talked to you already, but not at the expense of being creative. If you're too rigid and too, for instance, I've talked to some people that went through DOE training, and all they would ever run was a 3 or 4 input variable full factorial, and that's all they would ever use. And that was just, it hampered the creativity because ultimately the problem needed about 7 variables. Again, some people teach with a flair for the elegance of the mathematics, which makes it appear complicated, but really not so much. And again, you can use hardware or computer models to generate your data. I see a lot of stuff talking about software. I see SPSS and Minitab reference. I don't see others. I noticed on SPSS, Minitab. SAS has a software called Jump, GMP. The ones that I think are best, I think I have a slide in this at the end, but I'll tell you now. Minitab is acceptable. The Jump software is acceptable, but it tends to be more of a power user, someone that's using Jump on a consistent basis, get through there relatively quickly. Both Minitab and Jump are kind of clumsy and time consuming to use. The best software out there I haven't seen listed here yet is by a company called Staties. They have a software called Design Expert, and that is the fastest software to perform. It's the most powerful. And at the same time, you can pick it up 6 months after doing your last DOE and still get through it really easy. So to me, the Design Expert Staties software is the best, with Minitab and Jump being a second tier, but also very good, very strong. And I've given all 3 companies feedback on what they need to do to get better. I've trained other DOE softwares as well. They just are, yeah, it's another tier. And I do frequent software reviews to see what's out there, see if there's anything new. And those 3 continue to make the, over 20 years of watching software, I've never seen anything break the top 5. So I talked briefly, and we got 10 minutes. I see a question from Dennis about software, and we'll talk more about software in a little bit. 10 minutes, so I want to get through a couple of these things, but I'll for sure address that question. Here's the DOE process I was referring to earlier, where you define the goal in words. The response is your technical measurements, knowing if you're making progress. Third step, listing every variable and then picking the critical few to include in your DOE. Fourth step is picking the appropriate tool. There's a lot of them out there. And that's one I have it starred because that's where the software helps you. Select safe and consistent test levels that fit into that matrix. Because you have multiple output variables, you need to address the trade-offs. What are top priority outputs and what are lower priority? Execute your test, analyze it, that's where software again helps you. And then next step of test. So you've run through this DOE once. Do you need to do a second DOE to learn more? Are you ready for a verification test? Or are you going to do a complete redesign? So that flow, and I have videos out there on YouTube that discuss more about this process, but just from a high level, that's the process I teach to all the time. So I was going to ask what DOE tools you're aware of, but since we're kind of crunching up on time, I'll leave that out. Here's the basic tools of DOE. Factorial tools, The full factorial is every combination of the input variables using two conditions, say 10 psi and 15 psi, restricting to those two, which is not a huge restriction in practical application. But if that becomes hard to manage, which happens 5 input variables and above, and I recommend usually never going above 9. I find that most projects are 3 to 7 input variables. So if you're in the 5 to 7 range, these fractional factorial tools are a way to strategically reduce the combinations, but still get the information required. The Gucci approach is that typically in application maximizes the assumptions of the fractional, so you have to be careful with that. And that's kind of the core. In every tool of the ones that I mentioned, software tool, they all have that available. I actually have put a template for 3 and 4 input variable full factorial DOEs on my website. You can look at that. So that's just an Excel spreadsheet that you can use to quickly do some analysis, simple analysis. If you look at the, I talk of them as advanced designs, response surface methods. 3 level for each input variable, or 5 level, and then optimization techniques, numerical and graphical. You saw in the case study that yellow overlap was a graphical optimization technique. Then there's some related statistical tools which aren't really DOE, but I think are important because we're still gathering information strategically to reduce risk. So, gauge R&R, Monte Carlo analysis, and SPC are things heavily related and tie into DOE a lot. Dennis talks about fractionals may also be screening experiments. And at least in my language, screening is a fractional factorial that's been minimized the number of test runs as much as possible, which can be a risky approach. And Fred mentions about the value of gauge R&R. I've been brought into clients to do a DOE for them. And the first thing we had to do was do a DOE on the measurement system so we could pass a gauge R&R so we could actually know where our performance was on this product we were developing. It was a medical product. It involved animal studies. So we were doing stuff on the bench to avoid the animals and just developing that bench test so we can be smart and humane in what we were doing. That's just a quick look at the tool list. I apologize, I don't have a software slide in here. I've already mentioned it, and Fred gave the link to Staties. Staties is a DOE-only tool, so it's going to do these full and fractional tests. It also is capable of doing Taguchi, 3-level, 5-level, and optimization. It actually can plug in as well and do some Monte Carlo work. A tool like Minitab or Jump, they can do all the same things at a slightly reduced level compared to Design Expert. But Jump and Minitab also, and this I think was, let's say the right person, Dennis said, it's a comprehensive general purpose package, Minitab and Jump are. So they do the DOE plus they'll do gauge R&R, they'll do process capability, they'll do t-tests, they'll do non-parametric tests, they'll do a whole range of other things as well. So when I do, personally, and I have all 3 softwares, but when I do hardcore stats, most companies I find are using Minitab, so I tend to do that to be in step with them and can file share with them. My design experiments work is always in Design Expert. If they mandate Minitab, I've actually found it quicker to analyze it in Design Expert first, and repeat it in Minitab, and that's quicker than starting in Minitab for me. Then I can give the file share in Minitab form. And then Jump, I haven't used as much. It's incredibly powerful, very graphically driven. But again, the people that tend to use Jump Minitab, people kind of come and go with using it, but Jump, what I found, people that use it tend to be the people that are doing statistical analysis, quote unquote, 8 hours a day. Um, when I do my development work, I'll have a heavy analytical phase, say for 2-3 months, and then we're, um, say doing drawing review and procurement for another 2 or 3 months, prototype building testing for another 2 or 3 months, and you're not on Minitab during that time, and that comes. So when it comes and goes for usage like that, Minitab you can usually fairly quickly pick up. Design Expert you can pick up. To utilize the full power of Jump software takes using it continually over time. Yeah, and yep, to Dennis, and that's why I've trained with so many different things. Um, if you're currently using Minitab, I'll train you how to use Minitab and talk you through that. If you're already using Jump, use that. Using what you're familiar with and have access to is a key. Again, there's been other companies that they see what Design Expert can do, and I'm like, you guys don't even do Excel analysis right now. So if going to something like Minitab or Design Expert for them would be a huge jump. So I worked with them and we found an Excel add-in tool that does, the Excel add-in tool could do more stuff than Excel could on its own, or at least easier. It could do some rudimentary DOE, and compared to the culture of the organization, that was a massive step for them. So like what Dennis just commented in the chat window, yeah, Excel is crude. The add-in to Excel was a step in the right direction. Minitab would be another step, and other softwares could be another step. And then from a DOE point of view, if you're already killing it with Jump and Minitab through your company, you might want to, and you're doing DOEs constantly, which happens a lot in the medical device world, then it's probably cost effective to train in and use some others. Add in Design Expert software to really up the performance of your team and efficiency of the team. Sean just asked, which Excel add-in did we use? I can't remember offhand. I believe it was SPC for Excel. Excel is the name of it. I could be wrong. So shoot me an email, Sean, and I'll dig it up and make sure. I don't want to waste people's time searching for it. But Dennis makes a good point about validating software, which I've done before. Yeah, Sean, if you shoot me an email, I can give you the name. I have it listed. I know I can't find it quickly. But yeah, to Dennis's comment about validating software, and using textbook examples, and I would say be careful which textbook you use. I found some errors in textbooks, but yeah, use some a solid reference. We talked in the intro about George Box. George Box has multiple books out there. He's passed away now, but his stuff is pretty well screened and used. So I would assume that those are an example using those. I've used several of them to validate and check that they work really well. So with that, I see we're at 12:01, a little bit over, but I got in the core of what I wanted for you to think about, of how to think about, do I need it, or do I need DOE or not? And understanding just kind of risk idea, and yet still play a little bit early to gain just a feel for what your product is doing or your process, whether it's a manufacturing example, product design, there can be software applications, there can be marketing applications for DOE. I've done all of those. So anything's possible. It just needs inputs and outputs that you have uncertainty about. If you know the solution, just do it. If you don't know the solution, you need to create one and gain understanding. Go ahead and do that. Fred just put up a link about online course coming up on DOE. Gives you the next layer of all of what we talked about today. So, you know, if you're interested, if you have questions about that, let Fred or myself know. Otherwise, hope to see you through that process. And either way, good luck in your testing, your experimenting. Unless there's other questions, I'll let Fred wrap up.
All right. Well, thanks, Perry.
When I do, I shared my
Yeah, please
contact.
do. Put your
Sorry, Fred. I shared my contact info. If you want have questions, I always tell people if it's a 10-minute question, it's always free. And if I'm curious, I may go up to an hour. So, that's obviously a little bit of humor, but you know, call, email if there's simple little things that are holding you back and you want a simple answer. I'll certainly give that to you. Don't worry about that. Um, I enjoy connecting with people. It's a very small world. I know Nathan on here emailed that a friend of mine told him about this webinar, and that's why he's here. So it's a very, very small world, and I'd like to help out when I can.
all right. Well, thanks, Perry. I'm going to go.